All right, so we're going to start physics today, and we will probably be doing physics until after May long weekend. Probably somewhere in that area, because I mean, obviously we have a week off coming up, okay, and you have an exam next week and stuff like that. So we're kind of just going to get into it before we have a break, and then we have some time after that where we'll be working on it pretty heavily. But it's a pretty long unit, okay, kind of like chemistry, and the last unit is really short. Okay, like last semester, because we lost that week, I taught it in 3 days. I don't want to do it in 3 days again, but that was necessity. Okay, so we've got that kind of coming up. That last unit should take us about like two and a half weeks. Okay, so like I say, end of May is about when this one should finish up, and then June will be the last unit, and then we'll have exams, like the exam schedule. And like I said, I don't know when your other exams are, but yours is June 22nd at 9. Okay, so just make sure that you've got that on your calendar. All right, for physics. So physics studies the movement of objects and the reasons why those movements happen. All right, we are going to specifically look at energy in a number of ways. But we are also going to look at graphing. Okay, how many of you have taken Math 10 already? Okay, how many of you are taking it right now? Okay, good. So the stuff that you did in Math 10 with like graphing and like y equals mx plus b, we're doing all that again. Okay, so that'll be hopefully familiar to you, but we'll be using that a bit in this unit, and there'll be a fair amount of algebra in this unit. So you're going to need a calculator every day for this unit. Okay, so if you haven't got one, okay, make sure you get one and bring it. It doesn't need to be fancy. Okay, just the cheapest scientific calculator you can find will do the job. Okay, unless you want to get yourself something fancy and treat yourself, that's entirely up to you. But you do not have to go out and spend gobs of money. Okay, you just need a simple scientific calculator for this. All right, so today we're just going to look at the types of energy, kind of the history of energy, because energy is what makes everything happen. Okay? Energy is the ability to do work, and work is what is what we actually see. Okay? We can't see energy. Right? Energy is not a material. It's not something we can capture in a jar and measure, okay, or anything like that. And that's actually what made it difficult to study for so long. Okay, people had this idea of what energy was, but there was no way to really prove it because it wasn't a material. Okay? It's easy to prove stuff about chemistry and biology because you're dealing with either living things or actual materials. But with physics and energy, it's tougher because you have to conceptualize it. All right? I can't hold energy in my hand necessarily. Okay? I can see the effects of energy, but I can't necessarily hold it in my hand. It's not something that I can measure or touch or smell, okay, or anything like that. So it's more difficult to kind of study and understand, but of course makes everything go around. All right, so this picture here is showing the Inuit blanket toss. Okay, the Inuit blanket toss, now mostly ceremonial, but way back in history, it was actually a hunting tool that the Inuit people used. Because where the Inuit live, okay, in the tundra of the Arctic, we're talking about a flat, almost featureless Arctic grassland. So imagine kind of Saskatchewan, kind of like that. Okay, you know, when you get to the border, you can see the Manitoba, kind of like that. Okay, but you can't really because the horizon kind of cuts you off. And that's the problem, is that with no cover of any kind, you can see in this picture, like there's no trees. Okay? The word tundra actually means treeless. Okay? And so there's no trees, there's no hills, there's nowhere to hide if you're trying to hunt something like, you know, a big herd of caribou, for example, okay? Which would have been one of their main food sources. So in order to know where their prey was before they ran off, what they would do is they would throw somebody up in the air so that they could see a little bit further than everybody else. Right? In other places, you just climb a hill or climb a tree, and you can see a little bit. You get that elevated position. You get the advantage of being up higher. Well, there was no way to do that. So what they would do is just take a blanket, everybody would stand around the blanket, they put the smallest person in the group in the blanket, and they throw them up in the air and catch them. They wouldn't let them fall. Okay? So while that person's up in the air, obviously they can see farther, they can maybe see the herd of caribou, the herd of caribou can't see them, and then it's easier to sneak up on them and effectively hunt. Okay? In order to do this, we're looking at the conversion of many types of energy. In fact, we're looking at many energy conversions to make this happen. Okay? So the initial energy for all of this comes from the people themselves. Okay? It's the chemical energy that was in the food that they ate. Okay? They use that chemical energy to contract their muscles. Okay? So they're turning that chemical energy into mechanical energy in the movement of their limbs. Okay? That energy does work on the blanket and the person in it, exerting a force on them through a distance that throws them up in the air. So their mechanical energy is being transferred to the blanket and the person, and that person's speed increases. Okay? That's a change in their kinetic energy. As their kinetic energy increases, eventually they leave the blanket. And now, the people that were moving the blanket can't do any more work on them, because there's no way to exert a force on them anymore. They're not touching the blanket. So their kinetic energy starts to decrease. They start to slow down because of gravity. Yeah, gravity starts to pull them back. So they slow down, but their kinetic energy is being converted into potential energy. The higher you go, the more gravitational potential energy you have. Okay? Until eventually they reach their highest point. Now all that energy that was initially the food that the people ate is now potential energy in the person in the air. Then that person starts to fall back down. Their potential energy turns back into kinetic, and the people down below are waiting to catch them. When they hit the blanket, the people absorb that energy. Okay? They do work in pulling the blanket and making sure the person doesn't hit the ground, okay? And that turns into heat and sound and other forms of energy that just go into the surroundings. Okay? So there's a lot of energy conversions in the simple act of throwing somebody up in the air with a blanket. Okay? And that's what we're going to be looking at, is looking at simple everyday things, but from the perspective of what kinds of energy might be involved. No, again, reliability is kind of not allowing us to throw people in the air. And don't try it at home. I never said you should try it at home. And I have that on record because I'm recording myself. So you can't go home and say, Mr. Coderre said we should throw people in the air, because I specifically said don't do that. All right. So when we're talking about forms of energy, okay? The definition of energy is the ability to do work. If you have energy, then you can do stuff. Okay? And by stuff, I mean basically anything. Okay? Because I'm sure you've all had this happen. It snows, you know, we get the snowfall warning, driveway, sidewalk, everything's covered with a foot of snow, and mom and dad say, hey, get out there and shovel. And you're like, oh, I don't have any energy, I can't do that. Well, it's a lie. If you're alive, you have energy, okay? You just don't want to. But if you literally had no energy, absolutely, you would be incapable of shoveling snow, because energy is the ability to do work, and shoveling snow is work, okay? When you shovel snow, you exert a force, you lift snow, you throw snow, okay? All of that is work, all right? And you have to have energy in order to do that. Everybody okay with that idea? Okay? So very specifically, energy is the ability to do work. Okay? That's something that could easily be a multiple choice question on a unit exam. Not this one coming up, but the unit 3 one. Okay, so a person who's run a marathon has obviously used up a lot of energy. Okay, they've converted a lot of the chemical energy in their body into mechanical energy that has propelled them forward while they run. Okay, that sort of makes sense to everybody? All right, so we're going to look at the different kind of forms or types of forms of energy, I guess we'll say. And we'll start with chemical energy, because chemical energy right now is still the dominant form of energy, okay, that basically drives society forward. Right? We still generate the bulk of our electricity in Alberta and Canada in general with the burning of fossil fuels. Fossil fuels are chemical energy. Okay? When you eat food, that's chemical energy. Okay? Any energy that is stored in the bonds of a chemical compound is chemical energy. Okay? Chemical energy, though, is potential. Chemical energy can't actually do any work, not until it's converted into something else, okay? Because it is, after all, just potential energy. It has to be converted to something else in order to do anything. So if we're looking at this molecule here, okay, this is C3H8, propane. We use it to cook food, okay, or run furnaces or heaters, stuff like that. Okay? When we burn propane, we release the chemical potential energy in it. Okay? Where is that chemical potential energy? In each one of these bonds. Everywhere where there's a bond in the molecule, there's energy. When we break those bonds, the energy is released. So when propane reacts with oxygen, when we burn it, okay, every single one of these bonds gets broken. And the energy that is in it is released. And it's released as heat. Okay? And then we can use the heat to do other things. Okay? Everybody all right with that? Okay? But propane itself doesn't do anything. Right? If I have a tank full of propane, that's great. There's a lot of energy in that tank. But it can't do anything until I release its energy by burning it. Okay? Everybody all right with that? Okay? If I'm looking at a big plate, with an awesome steak dinner on it, if you're vegan, it's something else, but okay, I like steak, so I'm saying steak dinner. It's Friday, can't have steak today. Okay? Big plate of salmon, okay, for today. And I look at that, it's got a lot of chemical energy. But it doesn't do me any good until I eat it, digest it, and then have the sugars broken. Okay? So the mitochondria in my cells would break down those sugars and release the chemical energy within them as heat, okay, and as some other things like ATP and stuff like that that my body can then use to do mechanical work. Right? So chemical energy is only potential energy. Right? And this part here that's underlined, that's important. So chemical energy is the potential energy stored in the chemical bonds of compounds, and it can be in things like the food you eat. Okay. Do all things that are chemical energy contain the same amount of chemical energy? Definitely not. And that's something that Antoine Lavoisier, okay, who was one of the people who came up with the scientific method, okay, realized when he was doing studies of basically burning things. So I guess if you're like a pyromaniac, this is a great kind of thing to study because he got to set stuff on fire. Okay, so he measured the amount of heat that was generated by burning equal amounts of different fuel. Right, so he would burn 1 kilogram of wood, and it would raise the temperature of the water in his experiment by a certain number of degrees. And then he would burn 1 kilogram of coal, and it would change the temperature of the water by even more, because coal is far more energy dense than wood is. Okay? And so on and so on. All the different things we have, okay, have different amounts or contain different amounts of energy. All right? Everybody kind of good with that? All right. Electricity and magnetism. So electrical energy is energy that's stored, or is not stored, is work that's done by moving charges, specifically electrons. So we can force electrons to flow, okay? We can use them to drive things along, right? That's essentially the way an electric motor works. Okay? The flowing electrons go through the circuit and they cause the electric motor to turn. Okay? So what we're using there is the kinetic energy of an unfathomable number of really, really tiny little electrons. Okay? As long as there's a way to get the electrons flowing from one pole to another in a circuit, then that circuit can do work. So if you plug it into the wall, okay, you've got energy flowing from one prong through the circuit, going back through to the other prong, okay, things like that. If you've got it hooked up to a battery, the energy would be coming out of the negative end and going in through the positive end. And you'd get your circuit doing work until the battery is dead. Okay, it's the same with your phone. When you plug your phone in, right, you're sending electrons into the phone, okay, and they are charging the battery. So they're basically making sure that the negative pole has more electrons and stuff in it than the positive pole, and then when you unplug it, it starts doing its work. Those things get closer and closer together until your phone is dead, and then you charge it back up again. Okay? As long as there's a difference between the negative and the positive side of a battery, it can do work. It's when they start to get balanced that they can't do work anymore. Okay? Because now there's no motivation for the electrons to flow in one direction. They flow equally in both directions. But if you make a real difference, or what we call a potential difference, between the negative side and the positive side, electrons will always try to flow and create a balance. Everything in nature seeks a balance, and we just take advantage of that. Okay? This thing right here, this is the great-great-great-granddaddy of the AAA battery. Okay? This is the Volta pile. All it is discs made of certain metals with moistened kind of paper, celluloid paper, put in between them, okay, and you've got them kind of stacked like this. When you stack them like that, they obviously, because they're metal and the paper between them is moistened, electrons can flow and you can create a circuit. Electrons will come out the negative end and go back in the positive end, and this could generate a small amount of electricity. Not much, like less than a AAA battery, but it worked. And it showed that you could convert chemical energy into electrical energy, which is what we do with a battery. Okay? Even your lithium-ion battery that powers your phone is still using chemical energy to generate electricity. Okay? And this is why. Anyone ever done the battery test? Like if you don't know if a battery's like alive or dead, what do you do with it? Okay, if it's a 9-volt battery, yes, you can do that. That was the way we used to check them when I was a kid. Like, you put the 9-volt because it had the 2 leads on the top. Okay, it's a little trickier to do that with a AAA. I don't know how you get your tongue on both ends of that, but probably wouldn't do anything anyway. Okay, but with a 9-volt battery, you could do that and you get a little like tingle across your tongue. If you didn't get a tingle, then the battery was dead. But how can you test like a AAA or a AA battery? Okay, put them in your remote. Yes, you could do that, but even quicker than that. Battery test. So you guys have all these things that work for you, and when I was a kid, we didn't have those things. Do the drop test. Okay? If you drop it and it tips over, it's good. If you drop it and it stands up, dead. Okay? Because as the electrons move from the positive end to the negative end, okay, you actually start getting a change in the distribution of mass of the battery. Okay? If it's good, then you'll have more, sorry, it's the other way around. Now I can't remember which way it is now. Anyway, when you get the battery to one point and all the weight's at the bottom, right, then it'll stand when you drop it. Okay? And if it's gone the other way, most of the weight will get to the top, and then when you drop it, it'll tip over. And you can test it. I can't remember now which way it is. Positive one's on the top. It's on the positive end. Dead. So if it falls over, it's dead. I think that's how it works. Okay, so electrical energy can be turned, or chemical energy can be turned into electrical energy, and it's just the moving electrons that do the work. Okay? Now, there's a big relationship between electricity and magnetism. Okay? Because electricity and magnetism can cause each other. Okay? Electrical currents can create magnetic fields, and magnetic fields can be used to generate electrical currents. If you have a wireless charger, that's how it works. It actually uses a magnetic field to generate an electrical current that will charge your battery without it being plugged in. Okay, so if you have a wireless charger, it's basically a magnetic field that surrounds it that can make the electrons flow in the right direction. Okay? This was kind of discovered by accident, but a guy named Oersted was just kind of doing some experiments, and he had a current carrying wire, like, and it was carrying a lot of current. And he happened to have a compass nearby for whatever reason. Okay? And when he found that when he looked down at the compass, it was sitting right underneath the wire. And he looked at it and it wasn't pointing north. It was pointing parallel to the wire. And so he picked it up to look at it, and as soon as he picked it up and moved it away from the wire, it pointed north again. And then when he moved it closer to the wire, it went parallel to the wire. Okay? And what that means is the flowing electrons in the wire create an area of magnetic influence around the wire. Okay? So they would create a magnetic field, and that magnetic field affected the compass. Okay? In the same way that if you put like a magnet next to a compass, you can make it do whatever you want. Okay? Or if you have like even a big piece of metal or iron or steel near it, it'll kind of go towards that. Okay? Because those things are going to generally be stronger than the Earth's magnetic field because they're so much closer to it. So he discovered that electricity can produce magnetic effects. Okay? Made the first electromagnet. This is also how radio transmitters work, how the transmitter and receiver in your phone work. Okay? They are things that produce magnetic fields. Okay? And you may have also heard, some people are like, oh, you don't want to live near power lines because it can cause cancers and brain tumors and stuff like that because there's this magnetic field around them. There's a magnetic field, certainly, around a power line, but its strength decreases exponentially with distance. That means if I'm right next to the wire, the magnetic field would be very strong. If I move 1 meter away, it'll decrease. If I move another meter away, it'll be half as strong as when I was, it'll be 1/4 as strong as when I was 1 meter away. If I move back again, it'll be like 1/16 as strong, and so on and so on. So it decreases exponentially as I get farther away from the wire. So unless you live on the wire, you're okay. Okay, like it's not going to hurt. It's the same argument with cell phone towers. People say, I don't want to live next to a cell phone tower because it'll cause brain tumors. Well, if that's the case, then don't use your phone either. Okay, because your phone is like right next to your head very often. All right, I would be much more worried about my phone doing that than being near the cell tower. Okay, so people have these kind of strange ideas about that. Okay. The other thing we discovered is that this also goes the other way. You can use magnets to produce electricity. Okay, that's kind of how your wireless charger works. Okay, but if we make a coil of copper wire, we put it onto a voltmeter, okay, and you put a bar magnet through that coil of wire, you'll get a current. Because the magnetic field that surrounds the bar magnet pushes electrons. Okay? Electrons are kind of repelled by the magnet. And so when you push the magnet through the coil, the electrons that are in the coil try and run away from it, and it creates a current through the wire. Okay? This is how generators, alternators work. Okay? We get a magnet that's going back and forth, back and forth, back and forth through essentially a big coil, and that's going to produce alternating current or electricity. Okay, so little things in here to know. Oersted discovered an electric current could produce magnetic effects, and Faraday discovered the opposite, okay, that a magnetic field could produce electrical effects. Let's just make sure you've got those things underlined there. All right, so around this time, people are like, okay, so there's lots of ways to produce electricity and lots of ways to produce magnetism. Can I produce electricity with heat directly? Okay, and so Seebeck tried it. And what he built was something that was based on what Oersted found, that if I have a current carrying wire, I'll produce magnetic effects. So what he did is he essentially put a compass needle under a piece on this apparatus here where he had an iron bar and then kind of a copper plate that went above it. And what he did is he heated up the iron. Now the reason that this makes an electric current is because iron and copper heat up at different rates. So when he heated up the iron, the molecules inside the iron or the atoms inside the iron start to move faster and they run into each other. Okay? And eventually that would get to the copper. But the heat would be transferred through the copper way faster than through the iron, and so it allowed particles to start moving, which was an electric current. And when he did that, he found that the compass needle went from pointing like this to moving in line with his apparatus, okay? Showing that heat was in fact producing an electric current. Now, this is not something that we use to generate large amounts of electricity because it's highly inefficient. It takes a ton of heat to produce even a very small amount of electricity. Basically, what we use this for is two things. We use it in circuit breakers. Okay? Anyone ever pop the breaker at home? Plug too many things into one circuit and the breaker pops and you gotta go downstairs and flick it. Okay? That's caused by what we call a thermocouple. As the circuit starts to heat up, it generates enough of electric current to pop the breaker open, okay, and then protect the circuit from overload and protect it from starting a fire. Okay? And we also use it in some models, not all models, of hybrid and electric vehicles. We put it in the brakes. So we put a thermocouple in the brakes, in the brake rotors of hybrid and electric cars. And then every time you hit the brakes and the brakes squeeze and it's metal on metal, does it get hot? Okay, so that thermocouple takes some of that heat and turns it back into electricity, which is sent back to charge the battery. Okay, it's not a lot, but it's a little bit. It extends your range. It makes it more efficient. It wastes less energy because your brakes basically waste energy. That's what they're for. Okay, they're designed to take the mechanical energy of a moving vehicle and turn it into heat and sound so that you can stop. Okay, but in this case, it can capture some of that heat, turn it back into electricity, and recharge the battery. Again, you're not going to be able to drive forever. This is not a super efficient method of recovering energy, but it recovers some energy. All right, nuclear and solar energy. Okay, so on Earth we have there are two types of nuclear energy. The kind that splits atoms and the kind that forces them together. Fission and fusion, right? So we generally use nuclear fission. Okay? Nuclear fusion is something we're trying to get towards because it would be far more efficient and would have very few waste products compared to nuclear fission. Okay? But right now what we have is fission. So in fission, we obviously split the atom. We talked about that in Unit 1. And it generates a lot of heat. That heat is then used to boil water and turn it into steam, and then the steam turns a turbine. So essentially, all electrical energy is generated that way. Either you use a nuclear power plant to make heat, or you burn coal to make heat, or you burn natural gas to make heat, whatever. The bulk of our electricity is generated by using thermal energy of some kind. Okay? We don't use a lot of nuclear energy here in Canada, even though we do produce our own model of nuclear reactor. We don't use a lot of it here, but a lot of European nations rely almost entirely on it. France, their electrical grid is almost entirely powered by nuclear power. Okay? But we use a lot of hydroelectric, we use a lot of chemical energy, okay, and we're converting more and more things to wind, okay, like wind power and solar. Okay? What's the problem with wind and solar?
It doesn't last forever.
Doesn't last forever, yes, and
They're DC, aren't
they are DC, but they can be converted to AC. Yeah.
And it's not always windy, it's not always sunny.
It's not always windy, it's not always sunny. Okay? You can always rely on a coal plant or a nuclear power plant to be on. Okay? As long as there's fuel, they can run. But the wind farms down in Pincher Creek, even though it's like windy all the time down there, okay, it's not windy all the time down there. And it's not the same amount of windy all the time down there. Okay, we actually have our trailer down near Pincher Creek, so we actually drive past the wind farms and we can see the wind turbines from our campsite. So we can, I've kind of observed how often and how fast they turn, and it isn't consistent at all, right? Some days they're going like crazy. You can actually hear them humming, okay? And there's other days where they don't turn at all. So if I'm reliant completely on that form of energy to provide me with electricity, there are gonna be days where I sit in the dark, okay? Because it's not windy enough to turn the turbines. So it's great in that it's clean, there's no carbon footprint, okay? There's no, emissions or anything like that, but it's also not 100% reliable, okay? And it's the same with solar power. Solar power is wonderful as long as the sun is out. Okay, does anyone have solar panels in their house? Or use solar panels anywhere? Okay, so it's not very big in Alberta. We actually have a couple of solar panels on our RV that charge our batteries. We never have to use basically anything to keep our batteries charged and provide us with electricity. Two 200-watt solar panels will provide us all the electricity we need to power our small trailer. Okay, it would never work on our house because obviously you can't run like a microwave or a clothes dryer or something like that on that amount of electricity. But it's practical. We also don't stay in it in the wintertime when there's only 6 hours of sunshine because that wouldn't be enough to replenish what we would use.
How clean is nuclear energy?
In terms of your carbon footprint, incredibly clean, because you don't burn anything. In terms of the waste it produces by volume or by mass, also quite clean. There's not a lot of material waste produced by a nuclear power plant. The problem is the material waste it does produce is really, 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 really bad. Okay? It's radioactive, it's hot, and it can't be stored just anywhere because if it leaked or something like that, then you've got radioactive material out there, and that is incredibly bad. So all of the material that comes, all the waste material from a nuclear power plant has to be disposed of in a special facility, and there are only a few of them in the world. And they are basically a really deep hole in the ground that they will put the nuclear waste in and then fill up with concrete and then walk away from it, because it will be thousands of years before that nuclear waste is no longer radioactive. Okay, so that's kind of that's the trade-off, right? Is nuclear power is not going to produce any greenhouse gases. There's not going to be any water pollution or anything like that with nuclear power. In that way, it's very, very clean. And your support, like you don't have to have trucks or trains coming in all the time with fuel. Right? One shipment of fuel will last months. So there's those benefits. The carbon footprint of a nuclear power plant is far smaller than anything else. But what comes out of the nuclear power plant is like insanely bad. Right? And as long as you're careful with it, it's not really a problem. But we do have to dispose of it somewhere.
Power plant goes to food.
Well, and that's the reason why Canada doesn't have very many. There's this whole idea of not in my backyard, right? Well, yeah, like Fukushima, when the tidal wave hit, like there was radioactive material washing up on the coast of BC.
But wasn't it the only two times it happened was mostly due to human negligence for
Yeah.
care?
Yeah, the problem is that that's human nature too. And so the worry is that at some point a nuclear power plant is going to have a problem. The other issue with nuclear power plants, they're very expensive to build and they don't last very long. Like you basically have to either completely recondition it or decommission it after like less than 100 years, probably more like 50 years. Right? Just because the stuff that goes on in there is really hard on basically anything. I mean, you look at Chernobyl, right? Like there's the elephant's foot. Yeah, reactor 4. That's the one that had the meltdown. Okay, there is this piece of radioactive material that's kind of slag. It's some concrete and some metal and some of the fuel material, and it looks like an elephant's foot, but it's really big and it's glowing hot and it's super radioactive. And they built like a big containment dome around it, okay, to try and contain it all, right? So yeah, when something goes wrong, nuclear power goes really wrong. Right? It's not like a nuclear power plant would ever blow up, per se. To make a nuclear explosion, you basically have to do that on purpose. And a nuclear power plant doesn't really work like that, but a nuclear power plant could have a meltdown, which means the containment vessels crack, and then the nuclear material spills out. It's not an explosion, but it's all radioactive release.
But Chernobyl was caused by an explosion. I think that's how
Yeah,
it had the meltdown, and then the water, they didn't have enough suitable water to prevent a meltdown. Same thing with Fukushima, they didn't have enough water.
Yeah. Well, the salt water from the tidal wave would come in and corroded something or affected something, and then the other pump didn't work or
Well,
whatever.
the reactors weren't well kept, so they weren't in good condition.
Yeah, and that's the problem, is like you have to, it costs a lot of money, and human nature is to take shortcuts and save money.
It seems like the one place you don't do that.
Yeah, I would agree with you. Yeah, it seems like, yeah, when you're messing around with the power of the atom, you should spend the money, but yeah, I don't make those decisions. They're above my pay grade. So yeah, nuclear power does have lots and lots of benefits, but it also has that really big drawback. Yeah, so, but again, you don't ever have to worry about like a mushroom cloud kind of a blow up from a nuclear power plant, but you do have to worry about the nuclear material getting out into the environment, and then it's out. Like you can't clean that up per se. You can clean up an oil spill. You can't really clean up a meltdown. All right, so that's one form of energy, the fission, the splitting of the atom. And then there's nuclear fusion, which we're studying very intently. Right now, we can make it happen, but it actually requires more energy to have fusion happen than we get from it. Okay? And the reason for that is the way we have to contain it. You have to contain a fusion reaction not with material, but with energy. You essentially need an incredibly strong magnetic field. And generating that magnetic field actually takes more energy than you can produce with the fusion right now. Okay? When we get that technology better, then fusion is like really the way to go. Or cold fusion, would be another one. We're working on it, but we're quite a ways away from that yet. One place where fusion happens all the time is the sun. Okay? The sun is one big giant nuclear fusion reactor. Okay? It is caused by the fact that the sun is big. In case you didn't know that. Sun's really big. Okay? This is the mass of the sun. 1.99 times 10 to the 30 kilograms. So that's 1.99 with 28 more numbers behind it. Okay? Huge. By comparison, the Earth's mass is 5.98 times 10 to the 24. That's several million times smaller. Okay? Actually, several hundred million times smaller. So yeah, it's huge. And because it's so huge, its own mass is so powerful, generates so much gravity, that it actually forces hydrogen atoms together. Okay? They're literally crushed together by the sun's incredible mass. Okay? And every time you fuse hydrogen atoms together, you get helium and a whole whack of energy. Right? Incredible amounts of heat. Okay? Coming from it. So that's what's powering the sun. People didn't understand that because when they looked at the sun, they went, oh man, that's bright. And then they went, it looks like a big fire in the sky. So they assumed it was like a fire, okay? Like a chemical fire that we would have here. You set fire to wood and it burns. They thought that's what it was, just up in the sky. The only problem with that is that given the sun's mass like that, if it was a chemical fire and there was actually oxygen in space to make it burn, it would run out after 5,000 years. Okay? But the nuclear fusion reaction can go for billions of years. Okay? Our sun's been shining brightly for 5 billion years, and it's probably got another 3.5 to 4 where it'll still be good. Okay? And then after that, it'll get ugly, right? Because it'll run out of hydrogen, and it'll start fusing helium, and when it does that, it'll swell, and it'll become a red giant, and it'll swallow up Mercury and Venus and probably Earth. Okay? But don't worry, that's not tomorrow. Okay, it's like 3.5, 4 billion years from now. It's totally not your problem. Okay, but yeah, it'll eventually happen, and then it'll run out of helium, and it doesn't have enough mass to fuse anything else, and it'll just collapse on itself and become a little white dwarf. Okay, our sun does not have enough mass to go supernova. Yeah, I know it's disappointing, right? Like it'd be super exciting to watch, except for that whole like total destruction thing. Okay, so that's nuclear energy. It's basically the energy stored within the nucleus of the atom. Okay. All right, what we're going to spend the bulk of our time on is motion and energy, or what we call mechanical energy. Okay, so mechanical energy is the one that's the most important for this unit for us. Okay, and that is an object's total kinetic and potential energy. Okay, so whatever energy it has due to its position or condition and how fast it's going. Okay, those two things can affect an object's total mechanical energy. Okay. So, does that water bottle have any mechanical energy? It does. What kind? It has potential energy. It could fall. If it falls, it'll speed up, and then it'll get kinetic energy, and that can do work. So right now, it doesn't look like it's very energetic, and that's because its energy is potential. It could do work, but it has to be converted first. Okay? If I picked it up and threw it, then I will. But then it would have kinetic energy. Both still mechanical. Okay? Mechanical energy is the sum of both types. So if you throw a ball, okay, that ball has both kinetic, because it's moving, and potential, because it's above the ground, energy. Okay? And we have mechanical energy, right? Does this desk here right now, does it have any mechanical energy? No. It's not moving, and it can't fall. It's already on the floor. Okay? That desk has no ability to do any work. Okay? Does that sort of make sense? Okay? If I was to lift it above my head in an incredible feat of strength, then it would. Okay? Then it would have mechanical energy, because I would have done some work on it. Okay? To pick it up would require me to do work, and work is a transfer of energy. I would transfer that energy to it, and then it could do work. All right? Everybody okay with those ideas? All right. We will call it a day there, and we will pick up with Newton's cradle. That's that thing. Nearly got Newton beheaded. Tell you why. On Monday. Yeah, I know. You look at that and think, really? That nearly got him beheaded? But people were really afraid of things long ago. They thought he was a witch.